Learning Outcome 10.9. Determine the stability and causality of a system based on the region of convergence, and relate this to the corresponding impulse response. In the introductory videos on Chapter 10, Learning Outcomes 10.1 and 10.2, we compared continuous time and discrete time, and we saw that our Laplace transform had an e to the j omega, whereas our z transform had a z. Let's consider this in the complex plane with real and imaginary axes. We have our Fourier transform when we are on the j omega axes. We know that the relationship between our Laplace transform and our z transform is that z is e to the j omega. Well, the magnitude of z is equal to the magnitude of e to j omega, if we put magnitudes on both sides, and that's just 1. And the angle of z is just going to be our omega. Our z transform, therefore, when we're trying to do our mapping to produce our discrete Fourier transform, is going to have a magnitude of 1 and an angle that varies, and this means our unit circle. Our discrete Fourier transform from Chapter 5 is just the mapping to this unit circle. Now let's go back and do some other comparisons. In our Laplace transform, whenever we talked about a region of convergence, we were talking about the real part of our complex variable s. We said that a system was causal if and only if the real part of s included positive infinity. So given a pole, we draw a vertical line and the whole region greater than that particular pole. If it included plus infinity, that meant that that region of convergence would be one corresponding to a system that is causal. We said that the system would be stable if and only if the real part of s included the j omega axes. So therefore we need to have a region of convergence that includes our j omega axes. We said that as we move from continuous time into discrete time, that our j omega axes becomes our unit circle. Our Laplace transform is our z transform. And instead of the real part of s, we're always going to compare the magnitude of z. Z is this complex plane. We said that z is going to be e to the j omega. And if you were to take a complex variable course, one of the things you'll learn in there is about conformal mappings. Because we're talking about complex numbers here, this would be a conformal mapping. This would take our j omega axes and bend it, taking this plus infinity, wrapping it around into a circle connecting to the negative infinity, and this area that was over here at negative infinity would then become 0, because e to the negative infinity is 0. So we form a circle, taking this guy here and mapping into a circle, it maps into this. Notice that areas are not equivalent. What was over here in the left-hand plane is now the area inside our unit circle. We have a similar definition for causality for z transforms. A system is causal if and only if the magnitude of z includes plus infinity. That means we're going to have a boundary, magnitude of z, and if that goes outward towards infinity, then this region of convergence would be causal. Similarly, we have our stability if and only if the magnitude of z includes our unit circle, just like including our j omega axes. So this region of convergence would be stable.